Yes, I can. So it's okay. I'm sorry.
Here. Okay, thank you. So, hello everybody. I'm Pierre Berthaumieux. I'm professor in plant physiology, also in plant molecular biology, a little bit of genetics at Institut Agro Montpellier. And I am going to introduce you about, or to remind to some students, it depends, about iron nutrition and iron uptake by plants. Why? Because this will be one of the practicals, or the practicals that you will do during the summer school. And I will give you some basis to be able to put that in a more global view, and also to be able to interpret the results if necessary once you will have some of them. For those who want to follow the slides, I put them on the Moodle platform, so you can you can have them right now if you want to add something on them. And my presentation will be more or less detailed in greater, corresponding to the two papers which are also on the Moodle platform. So at least the first part of the Lee et al. Paper, and also the Rob et al. Paper concerning the coumarin accumulation. So these two papers can be considered as supports of my presentation. So as I told you, the presentation of these slides come after the course that you had with Germain Montazo about the tragedy of commons, and this is the last slide that he gave me, in which he introduced Arabidopsis thaliana, a question related to iron, etc., and coumarins. I'm not able to discuss about tragedy of commons, but as I told you, I will speak you about the mechanisms involved in iron nutrition in plants, putting the coumarin role in the framework of the whole types of responses that can be observed for plants. So first, starting with the iron concentration in soils. So iron is an essential element for all organisms. So bacteria, fungi, plants, humans, animals need iron. And it is the fourth most abundant element on Earth, so we should not really bother about that. Except that it has a very limited bioavailability. That is it is very difficult to get it for the plants, for the bacteria, for the fungi. So the animals is different. They eat other animals or they eat vegetables. So this is the way they obtain iron. But for plants and bacteria, they have to get the iron from the soil. And iron is the bioavailability is very low. So this is why iron deficiency is widely spread, and you can see it on this picture. I will use this picture 3 or 4 times in my presentation. But so this is a soybean field, and you see that the plants are chlorotic, and this is due to the fact that iron is poorly available in this field. And thus fertilization is often necessary to improve the production, the field production. So alternative ways could be developed through having plants which are more able, which can more easily get the iron from the soil, and this could be one of the reason to study what is going on and to use the information that I will give you maybe for breeding. So why is iron poorly available? Mainly, iron make complexes with hydroxyls, ions, and these iron hydroxyls complexes are solid compounds, and thus the iron is not available for the plants. So you see that if you increase the pH, the iron is associated with these hydroxyl compounds, and it precipitates. Now, this does not mean that you have no iron at all, because all these are chemical equilibriums. So this is why you have a very, very, very low level of iron available, but it's never zero. So this is one of the first reasons why iron is not available. And you can understand from seeing such a graph that by acidifying the soil, you may go towards acidic pH. It's not necessary to go to pH such as 0, 2, and 4, and at 0, 2, no plants can grow. But if you go to more acidic pH, you increase the proportion of iron which is available and not associated to hydroxyl ions. So this is one of the reasons why iron is not easily available. Other reasons are that iron is also chelated to other compounds. So phosphate is a good example. When you have a chelate between phosphate and iron, it's very difficult to solubilize it to make solution of this compound. And phosphate is trapped with iron, and it is difficult to separate them. More generally, if you are interested, if you analyze what is going on in the soil you have different charges due to the silicates and organic compounds which are present in the soil. And again, depending on the pH, the negative charge are more or less abundant. At low pH, the silicates and these organic compounds have no charge. And then iron is less prone to be associated to these compounds. In contrast, when you go to higher pHs, you have more negative charges, anionic charges, and iron can be associated to that more or less. And it's more difficult to get it because of the complexes that iron can make with the clay-humus complex. So this is a characteristic of the soils. They have different cation exchange capacities. And this, once they have a given level of cation exchange capacity, the pH is important to modulate this exchange capacity across the different pHs. Okay. So finally, the CEC as well as the pH of the soil influence the availability of the ions, the cations in the soil, also the anions, but we are speaking now about the cations, and in particular iron. So these are the main reasons why iron is not so easily available for plants in the soil, for plants and also for fungi or bacteria. So in response, what can plants do? Plants are able to modify their environment around the roots. For instance, here you have a picture of a tobacco plant. This is in vitro analysis, but it is to show you easily, finally, the ability of the plant to acidify its environment. So here the plant is grown in a substrate in which you have bromokerazole purple, which is an indicator, pH indicator. So this pH indicator is yellow when pH is below 5, and it is purple when pH is above 6.6. And you can see that here, depending on the medium which was used, you have a strong acidification, which is very located at very specific places in the root system. Okay, and this shows you a very high change in the pH that can occur more or less 2 units of pH between the yellow part and the more purple part. Okay, so this is a first ability of the plant, that the plant is able to change its pH environment. Here you have a second example. It's not pH, it's about reductase activity. So reductase is to change the oxidoreduction state in the environment of the root. So here it is shown for root, again, of tobacco with a marker which is methylene blue. So when this compound is blue, it means that it is under the oxidized form. And when it is colorless, it is in the reduced form. So you have here the ability of the root to change the oxidative status of methylene blue, and you can measure a more reduced environment compared to the neighboring environment in other parts of the root. So this is an example, more or less the same information, but presented in another way, concerning response of sunflower roots to iron shortage. So we come back here to iron shortage. So here you have the iron sufficient medium, and on the right, the iron deficient medium. And again, two markers are used. So here, a pH indicator, the bromocresol purple is the same one. And you can see that in response to iron shortage, you have induction of acidification in specific part of the root system. Okay, so this is a net efflux. It is the H plus ATPase, which excretes protons into the medium. Okay, so the idea is that, well, I will detail the idea on the next slide. Here it is the another marker which is used, so to measure the redox status. So here, it's not the same marker as previously shown. Here it is just to a compound which is associated to iron 2, and not on iron 3. So when iron is oxidized, it is under the form of iron 3, and it is not associated to batophenanthroline. But when it is reduced, it comes to be iron 2, and then this iron 2 can be associated to batophenanthroline, and the red color becomes visible. Okay, so this illustrates an iron 3 reductase activity to convert to make the conversion of iron 3 to iron 2. So now if we come, so these are examples of the way plants can modify their local environment in response to availability of elements. And the idea is to improve their ability to take up the corresponding elements. So for plants, two strategies for iron uptake have been described. So probably you have already heard of that if you have done a little bit of plant physiology before. So strategy one, which consists in acidifying the medium, as I showed you. This leads to solubilization of iron. Then there is a reduction step. And finally, the uptake of the reduced iron. So how is it working? So this is an example in dicotyledons and non-grass monocotyledons. So you have here an H plus ATPase, which uses energy to excrete H plus ions. These H plus ions interact with iron 3 chelates, and there is an exchange between the H plus, the proton, and iron 3, and the chelate associated with the H plus. So it's a chemical exchange between the two. And this leads to iron solubilization. That is, the association here is broken. You have the chelate on one side and the iron 3 on the other side. The point is that iron 3 cannot be taken up directly into plant cells. So I forget to mention that on the right part of this scheme, you have the interior of the cell, and the external part is on the left. So this is this is the soil, and this is the intracellular space. So iron 3 cannot be taken up directly. It has to be converted, so reduced to iron 2, and then iron 2 then can be taken up in the cell. So this was well described in Arabidopsis. So these are the names that were mentioned for Arabidopsis. In other species, names may change a little bit. So Fro2 is the ferrite reductase, which converts iron 3 to iron 2, and IRT1, it is a zip transporter, but also NRAMP1 to some extent are able to drive the entry of iron 2 across the plasma lemma from the outside to the inside. So this strategy is the main system that has been that the dicotyledons use to get to obtain iron. But and in some textbooks, the old ones, it was reputed to be the only way that dicotyledons were able to uptake iron. But more recent results have shown that in grasses, there is more or less the same kind of system, although it is not sufficiently well described so that we are not able to separate the different steps. So in grasses, what has been described, in particular in rice cell. So again, this is the inside of the cell. This is the medium, the culture medium. So the cells produce phenolic acids, and these are excreted in the medium through a transporter, a specific transporter. And this is not really well analyzed. These phenolic acids come in competition with the iron 3 chelates, resulting in a separation of the chelate from the iron, and also a reduction of iron 3 to iron 2. So maybe some pieces are missing, but this is what is known, okay? And then when you have iron 2, there are clear transporters which have been described in grasses, which are able to uptake iron 2 to iron 3. This was particularly described in rice because, as you may know, in anaerobic condition, when you have water in the field, it's very reducing environment, and this is one of the exceptional environments in which you have majority iron 2 and not iron 3, because it is anoxic and highly reducing environments. And then in this situation, the rice is able to take up iron 2 inside the cell. So this strategy exists in the different types of plants, although it is the main system that dicotyledon uses. And grasses, it's more opportunistic or depending on specific environmental conditions. The second strategy, which was described mainly in grasses for a long time, and maybe in the very old textbooks, it was the only strategy which was that the grasses used to get iron. This strategy consists in excreting a compound which would be able to chelate iron 3 and then to take up the chelate between this compound and iron 3. So again, this is the inside of the cell. This is the outside, the medium. This is the plasma lemma. So in grasses, the compound which is used it's produced is phytosiderophore. It's not the only one, but it's not one compound, it's a family of compounds. I will show you that later on. So these compounds are produced inside the cell. They are excreted in the medium through transporters. One is TOM1, but it's not the only one. And again, they come in competition with the iron 3 chelates, which are in the soil. And it's a matter chemical exchanges between different chelates. Phytosiderophore is a chelate of iron 3. If it is stronger, if it's Kd, the dissociation constant is higher, lower, it will associate to iron 3 in replacement of the other chelate to which iron 3 is associated. And then you create a new chelate, which is the phytosiderophore iron 3, and the other chelate, which was in the soil, is released. And then, once this is done, you have this new chelate, which is taken up by specific transporter YS1 and YS else being like. So YS likes, there is a family of compounds, of transporters, which are able to take up different types of phytosiderophore iron 3, because there are different phytosiderophores, and then different specificity of these chelates and the different transporters able to drive their entry into the cell. And then you have the iron which is inside the cell, and then it is used by the cell. So this was this second strategy, and recent. Oops, sorry. Okay, so this is the main system which is functioning in grasses. But more or less recently, let's say 5-10 years ago, a similar strategy was discovered in dicotyledons and non-grass monocotyledons. Again, the same picture. Here, it's not phytosiderophores which are produced, but it is coumarins. And these coumarins, alors, now, there are results about coumarins, but probably there might be other compounds, flavins and things like that. But here I show you the most known system, which is based on coumarins. I will show you what are coumarins later on. So these compounds are, again, like it is observed in the grasses. These coumarins are excreted in the soil. They are in competition with the iron chelates, iron 3 chelates, which are in the soil, and the consequence of that is that you create iron 3 coumarin chelates, and you release, you do not release anything, but the chelate which is present in the soil is no more in relationship, associated to iron 3. And then these chelates are taken up by the cells. So we know that it is energy-dependent transport, but up to now, we don't know which are the transporters which are responsible for this transfer. Again, there are several different coumarins, so maybe there could be 7 transporters, and work is ongoing on that. So this system exists, but it is not functioning at any time. It is particularly used in calcareous soils, that is with high pH. In high pH, you cannot use the previous strategy because the previous strategy is based on acidification. And when you have calcareous soils, you cannot significantly or sufficiently acidify the mediums to be able to release iron 3, reduce it to iron 2, and take it up. So in specific environments such as calcareous soils, this system takes the lead in dicotyledons and monocotyledons to take up iron 3 in the plant. So I come back to my picture, and here you can see that strategy 2 seems to be more efficient than strategy 1. Why? This is the cultivated soybean, so it's a dicot. It is fully, it uses mainly the acidification strategy, the strategy 1, and it is difficult. He has difficulty to get iron, while sorghum, which is a grass, easily gets iron in this field. So this is in an iron deficient soil, and there is the advantage of strategy 2 compared to strategy 1. This is not the only reason why it grows better, but okay, the response to iron is part of that. So 2 slides concerning the phytosiderophore first and the coumarins, and you will see that the situation is very parallel. So you have different phytosiderophores which can be produced. So here I show you a very simplified biosynthesis pathway, and the idea is not that you learn about the biosynthetic pathway. The objective here is to see that you may have different phytosiderophores, and here it is illustrated depending on the plant species in which they were observed. So nicotianamine, so you start from methionine, you produce S-adenosine methionine. This is a basic compound, a biochemical compound in the cell. Then what is specific to the phytosiderophore biosynthesis pathway is the nicotianamine synthase, which then goes into this pathway. So the first compound which is produced is nicotianamine. It is a more or less It is a compound which we can find in quite a lot of species. In particular, in Arabidopsis, this is the main phytosiderophore that we can find, but it is not used in Arabidopsis to catch iron in the soil. It is used in Arabidopsis to transport iron from the roots to the shoots or from cell to cell. Okay, so nicotianamine, which is more or less a phytosiderophore, is able to associate with iron and is involved in the root to shoot transport of iron, but not in the strategy 2 in Arabidopsis. Then from nicotianamine, you produce what people know as DMA, deoxymultigenic acid. And from that, depending on whether you are in barley or oats, and there are probably other changes in other species. I'm not specialist of this biosynthesis pathway. You may have different phytosiderophores which can play the role described in strategy 2 above. So you may understand that maybe if they do not use exactly the same phytosiderophore, maybe they cannot share, because the idea is that this phytosiderophore is created in the medium. It will associate to iron. You may have a competition. Is it the avenic acid which is more efficient than the muginoic acid, or the reverse, to get the iron? And maybe you have a kind of competition between barley and oats, which can be mediated by the chemical properties, specific chemical properties of the different phytosiderophores when they are in competition to get the iron. And you may have other grasses or other plant species which also produce different phytosiderophores which enable them to be efficient in the different environments in which they are grown. So what about the coumarins? So again, why I present you the coumarins? Because also it will be also presented in, you will work on that also in the practicals of the summer school. So very similar to the phytosiderophore, except that it has nothing to do. The molecules are completely different. So it is based this time on the phenylpropanoid pathway, which is a pathway, a very large pathway involved in quite a lot of secondary compounds, but mainly lignins, flavonoids, flavins, etc. And among these compounds, the feruloyl-CoA is one of the compounds which is also involved in the synthesis of lignins. So this is the basic secondary pathway that you have in all cells. Then from this feruloyl-CoA, you have a specific new biosynthetic pathway which produces the so-called coumarins. So again, this is not completely known. What is known is what is presented here. So you have, let's say, for instance, 4 genes or 4 proteins which are involved in the synthesis of different coumarins, the scopoletin, fraxetin, and sideretin. Okay, so these are the coumarins. This is an intermediate. There is another coumarin which is known, and I will show you some results with it, which is esculetin. But up to now we don't know what is the biosynthesis pathway of esculetin. We know that F6H1 is an enzyme which is necessary to produce esculetin, but we don't know whether it is from the same substrate or for another substrate. Okay, and then we don't know. Some research suggests that it could be. You see from the formula that it is a loss of methyl group can lead to the conversion of scopoletin to esculetin. So this is under research. What is interesting is that esculetin, fraxetin, and sideretin were shown to be able to associate to iron 3. Scopoletin is not, okay? So these 3 compounds are able to be associated to iron 3, although at different dissociation constants. The more efficient to fix iron 3 is fraxetin, okay? But it's much more efficient to associate to chelate iron 3 than sideretin or esculentin. And interestingly, depending on the pH in the soil, when you are at basic pH, okay, this gene is repressed and you have mainly fraxetin which is produced. And when you are in a more acidic environment, then this gene is activated and you convert fraxetin to sideretin, okay? So these coumarins, okay, they are able to interact with iron, but they have also other roles in the exchanges between plant and plant, between plant and bacteria. Some of them have antibacterial effect. So there is quite a lot of function that could be attributed to these different coumarins, and the choice to produce more one or the other one, which is highly regulated, depends on the specific environment in which the plant is grown. Okay? So if I make a summary on these iron uptake mechanisms, so what you have to have in mind is that all plant species can use both strategy to take up iron, what was called the strategy 1 and strategy 2. So this is not necessarily obviously so clearly presented in the textbooks. If you do not have the up-to-date textbooks, you may have a different view of the situation. Dicotyledons and non-grass model cotyledons favor strategy 1, and they use strategy 2 in calcareous environments, high pH, and this is what you will see in the practicals. In contrast, grasses mainly use strategy 2, which is reputed to be more effective than strategy 1, but they may also use strategy 1 in specific situations such as hypoxia, for instance. And both strategies, strategy 1 and strategy 2, are induced by iron deficiency. I didn't show you anything about that, but it is also a message that you have to have in mind. There was just a picture, one in the first slide, in which, in response to iron shortage, you saw the acidification and ferric reduction activity which were induced. So now I will give you 2 or 3 slides more directly linked to the practicals that you will be involved in during the summer school. You will have a detailed presentation by Adrian Westgeest. So I will not go into a lot of details, but I want to point 2 or 3 interesting, more general and interesting things about that. So all started by the analysis of one mutant, which does not produce, which turns out to not producing coumarin. So for those of you who are not familiar with plant physiology approaches, we like very much to start from mutants to have a screening procedure. So we are focusing on the mechanisms. So we are trying to identify a screening procedure to identify plants which do not behave like the common way. Okay, so we search for mutant, and the idea that a mutant usually is altered in only one gene, and theoretically all the other genes are not impacted. Well, practically it's a little bit different, but we have no time to go into that. So the idea is that you have a change in the phenotype, which is due to the alteration, the change in one gene. So here the screening was to analyze in calcareous pH, let's say pH, basic pH, pH 7.2, and to search for plants which displayed chlorosis. And often chlorosis, as I showed you on the general picture, on the field picture, is often associated to iron deficiency. It's not the only reason why plants are albinos or white, but are chlorotic, but it's one of the main reasons. So here you have the control condition in a normal pH, and you have the mutant which behaves more or less like the wild type. And here you have in more basic pH, in comparison to the wild type, the mutant is clearly chlorotic. And when you add iron in this medium, so under the high pH, with a very highly available form of iron. So iron with EDDHA is one of the least the least strong, the weakest chelates between iron and a chemical. And then in this condition, iron is more or less available, more available than in the control condition, at least in that condition. And you can rescue the phenotype by adding iron. So this shows you that this mutant is chlorotic at basic pH, and this can be relieved or saved if you add iron, and a very highly available source of iron. So, and then the author tried to identify what was going on, and they analyzed the shoot iron concentration. So this is in pH 5.6. This is in more basic pH, and this is in the when you add a source of available iron. So you can see that the mutant is in red and the wild type is in blue. And you can see that in high pH, you have a reduction of the iron uptake and an increase, a stronger reduction in the mutant compared to the wild type, but it is not zero, so there are probably other systems which exist. Huh? And when you give back iron, you more or less come to the origin and to the basic level, the expected level, and in the mutant you have a specific phenotype in which I will not detail here. So this confirmed that this phenotype was associated to iron accumulation. So in the framework of the practicals, up to now, it is forecast that you will do iron concentration measurements to assess the phenotypes or to confirm the phenotypes of the plants. Alors, I've put back here a short summary of the coumarin biosynthetic pathway. So this is the F6H1 gene, which is mutated here, and it is at the very beginning of the biosynthesis pathway. So you have more or less none of these. Okay, so this can be observed here. Here is an HPLC. So HPLC of the compounds in the roots. So the wild type is in black and the mutant is in red. And here you have, depending, so HPLC, you have different retention times. So you can see that in the wild type, you have esculin. Alors, esculin scopoline is the intracellular storage form of esculetin and scopoletin, okay? So forget that, it is a detail with no interest. So what is important is that both in the wild type, you have both esculin and scopoline, but in the mutant, you have almost no esculin and very little traces of scopoline. Okay, so this is to describe you what is this mutant. So what is interesting is that coumarin can be shared between species, and this is the reason why I presented you the previous slide. It is to illustrate what is going on here. So here again, you have the HPLC analysis of root extracts. And so this is the HPLC analysis. So this is the measurements of the peaks. And you do that in different plant species and you grow them in a soil which has no iron and which is basic. So what you can see is here from the standards are esculin, scopoline, fraxine, and scopoletin, 1, 2, 3, 4. What you can see is that, more or less, in none of these species, you have any of these coumarins. This is the mutant, which is shown. Unfortunately, in this figure of this paper, the wild type, the Rabiopsis wild type is not shown. But here you have in the mutant. As I told you, in the mutant, you have none of, you have no production of either of these different coumarins. So what you have then is that when you add fraxetin, so fraxetin is this one, okay? So you do a kind of a shortcut of the coumarin biosynthetic pathway. So you will have fraxetin, of course, and you may have sideretin if you want, okay? Or maybe depending on whether it is produced or not. What is important here is they analyze the fraxetine content in all these species. So the conditions, the growing conditions are the same, except that you add fraxetine. So what you can observe is that fraxetine is peak 3. So you observe fraxetine, interestingly, in the Arabidopsis mutant. So it is able to accumulate fraxetine in the tissues. But you can see that fraxetine can be also observed in tomato, where you had no production of fraxetine spontaneously. And the same in pine, where you had no significant production of fraxetine in this condition. And interestingly, you have no fraxetine neither in rice or maize, which are grasses. Okay, so it's interesting that in the dicots, a compound which might be produced by Arabidopsis mutants, by wild-type Arabidopsis, for instance, and which could be present in the medium, could be absorbed by tomato or could be absorbed by pine, meaning that you can share this coumarin between one species to another one. And the results here are not detailed enough to tell us whether this is linked to an increased accumulation of iron or not, if this fraxetine associated to iron or not. This was not detailed. This was one of the not a side project, but a kind of additional experiment which was done in this paper. But what is important for us is that if you can imagine that fraxetine can be excreted in the media because one of the plant species excreted it, other plant species can use it, even if they are not able to produce it by themselves. Okay, so this, I thought it was interesting in the framework of your practicals, in which you will see that we will try to associate wild type with mutant plants to see to which extent the wild type plant are able to help the mutant plant to get iron. And this is what was presented by Germain previously. So the take-home message at the end of this presentation is that so iron is present in soil, but it is tightly bound to soil elements so that it is poorly available. So you have more or less a lot of iron. You have significantly concentration of iron in the soil, but it is hardly available. And you have several organisms which compete with each other to catch this iron. You have the bacteria, you have fungi, you have plants, different species of plants, different varieties of plants. And they all have their weapons to try to catch iron. So the two strategies are more or less the same. Acidification to reduce the iron and uptake it. So the two strategies that I showed you, or chelation, but the different organisms, bacteria, fungi also, they put flavins, which are also able to chelate iron. So it's a big competition between all these to catch this iron. And also maybe some of them can catch the iron that has been released by others through releasing different compounds. So there is a diversity of compounds able to mobilize iron, the phytosiderophores, the coumarins, the flavins, and then it is the ability of some species to produce them, to put them in the medium and to take them back. So with problems of specificity, specificity of some chelates with irons with respect to others one that can also play a role in the competition for the acquisition of iron. And this is what I wanted to introduce to you. So that's all. I'm open for questions. And I can remind you before answering the question that there will be a 1-hour discussion session next Wednesday at 9 a.m. So feel free to ask questions.
Yeah, we can leave a little bit of time for the student to find a question. I have got one. So it was very interesting lecture. Thank you very much. So what you said that the coumarins are exchanged between individuals of different species. So that's completely new to me. And so, do you know? Have you any idea from the papers at which quantities those exchanges are made?
Alors, this is a plant physiology work. That is, it's not a real situation in a field, etc. The idea was just to illustrate the fact that this sharing is possible. So when you do such an experiment, um, it was not done through the co-cultivation of an Arabidopsis with another plant and trying to detect the transfer, etc. It was just in some of the work they analyzed which coumarins were released in the medium, and I found that fraxetin was one of the most important one, especially because it is highly associated. The dissociation constant is really low with the iron, and they were testing whether such a complex could be taken up by another species. And then they grow each species separately in a medium in which they added fraxetin. So this is the only work they did. And since this is not really a strong help to go further in the understanding of the mechanisms, which is what plant physiologists like to do. They want to clone the first, they want to be the first to clone the gene which is responsible for this or that and that. Nobody has up to now tried to go further to that. And in the practicals that we will do together, somehow we are not the first because we are mimicking a paper which has been published and which will be presented to you by Adrian. But the idea, initially, I would have loved to associate Arabidopsis with other plant species and to see to which extent it could be possible to do what you are mentioning, that is, helping other plant species to be able to grow in basic soil in the presence of poor iron availability if you co-cultivate that species with Arabidopsis. But I had no time to do that. It could be a nice project for students who would like to do that. By the way, I would like to remind the students that during the 1 week session here in Montpellier, you have on the Friday a time period in which there will be several subjects, but one of the subjects will be to write a proposal to go further what you will have done in the practical or what you have learned from this summer school. So ideas related to what Jack said and things like that could be a good support to write a proposal, imagine what type of experiments you could do to prove or not, to which extent one species can help another one, and to design appropriate experiment to do that and things like that. So it could be a good idea to have this in mind and to have this critical view and this competition view in mind to maybe to go further. It's not maybe.
Yeah, they will have time to think about that, but I'm very curious to see whether the students are able to make the link between your lecture about physiology and iron and what they have got as a theoretical point of view. I'm very curious. So how many of you have understood why this could be interesting to see this production of iron under the theory of the tragedy of commons? Who wants to either ask a question to Pierre, of course, or to tell me if they've understood the link between the two lectures or the many lectures? I'm very curious to see if we were able to suggest to you that there are some links very interesting in those lectures and to find example of strategy of command in plants or plant-plant interaction. So who is not so shy to try to make a first statement? So as nobody has his sound neither, it's so it remember me COVID, you know, when we had nobody's, you know, we had everybody online but no faces. So could you please, guys, open your cameras? So Hamza, thank you very much for connecting. So from what you have heard from the beginning, do you understand why we try to convince you that to look at the physiology and theory, to look at the Darwinian interaction between plants? So would you comment on that? Does it make sense for you?
Yes, it was very nice presentation, and it's very nice. Like you are integrating different sciences to prove this theory, especially from very deep dive into the physiology. So I'm really impressed, and it's very kind of a new avenue to search more on this stuff and to look in other species except Arabidopsis too. So it was very nice. And in the practical session of the summer school, I hope we will learn and deep more into it. And as you mentioned on the Friday, we have to write a proposal or the future impact about this. So we can write something very impactful. Thank you.
At least you're securing on that. I think that you can start making your neurons braining.
Yes.
It's very intriguing questions to me. I don't know for you, but to me, I was really impressed by one of the last slides of Pierre that I discussed, to see all that compound that could be exchanged, and because they could be considered as a common resources because it's about iron. So are they plant competing for that, or are they collaborating? That's terribly a deep question to me, but I don't know for you.
Yes, you're right. We have to dig about these topics. Let's see.
So any other comments?
Not really from my side.
Or questions, or particular questions, because maybe you have questions for Pierre for the physiological point of view. I had one. What is non-grass monocotyledons? Is that clear for you all, guys?
You know better than me, Jacques.
Yeah, but it was an open, naive question for the students.
Sorry.
No, it's okay.
Okay.
And I have a question regarding the summer school. On Saturday, we have a student symposium.
Yeah.
So in the student symposium, there will be different teams presenting different things like the...
Yeah. You will work on project by group on the Friday. For example, the one that Pierre presented you. And so you will work by group, and on the Saturday we will have a symposium, and every group will present his work or their work, and there will be a presentation and then discussion, and we hope that we are able to develop your critical skills and creative skills and every kind of skills we'd like you to get. And this will be the way we are going to put the marks. So it's very important. So you have to work during this session on all the points that have been given to you, because every lecturer has given to you a number of resources. So we expect you to read them and to have a feedback with them for the question and answer sessions. And once we will be in Montpellier, we will have time to discuss. And of course, you will have, I would say, we will accumulate knowledge and practical and ideas and thinking and whatever. And you will work by group to prepare that symposium. So the last day, it will be your turn to be lecturers.
That's great.
Yes, palm tree, you are right.
Okay, so if there is no other question.
I have another question.
Okay.
Regarding the report. First of all, thank you for the nice lecture. I must admit I'm not very knowledgeable in plant physiology, so I did not get all the points, but well, the breeding side I'm probably a bit more confident in. But I have a question regarding the report. So we were asked to do 2 reports on 2 topics until start of the physical phase, and I was wondering whether we will be assigned the topics or whether we can choose 2 topics. Yeah.
I think that somebody has tried to assign you topics. It was Dominique Tis, but I don't know if she published it on the website. Okay. So maybe she did. If she did not, I will go to seek for the information, and
okay.
My answer will depend on what she has done. So at the beginning, we thought that it could be completely free. for you to choose among the 2 topics among the 6 and to make it. But Dominique wanted to make you to work. But I have to ask her because I don't know if she did that. So
Yeah,
sorry
because
for
on the
that.
web page it said, on the Moodle page it said on 27th of June the topics should be assigned, but I couldn't find it at least. I asked also in the group chat.
Okay, you're right. You're right.
But
I think,
yeah.
okay. I will try to get the information and get back to you.
Yeah, okay, thank you.
Any other question? I agree, Pierre.
Okay.
Okay.
So thank you, and there will be a 1-hour discussion for people who want next Wednesday, particularly people who have been assigned or not. I don't know their subjects. So next Wednesday at 9 a.m. I hope it will be okay for you.
Okay, guys. I hope that it is so far so good for you, and see you for the next session. Will be the Adrians at the July 10th. So you will be more details about the experiment. So the session will be built on what the group of people that have been involved in the practical. So Pierre was at the first person. So it is a big work we are prepared for you, and the game will be that you have to get the idea of what we wanted to carry out as a scientific questions. So you will be, I would say, the police of scientific police. We will give you what we have prepared, and you have to decide what the question we wanted to address. So this will be your duty there, and we have for that. I hope that we will have the announcement of the Hans-Peter Pifo lecture about the experimental design that you will need. But for the moment, we have difficulty to get the news. So you will be announced too. It will be announced too. So have a nice evening, and thank you very much.
Bye.
Bye.
Merci beaucoup, Pierre, pour ta
Thank you,
leçon.
bye.
J'ai appris beaucoup de choses.
Thank you,
Je parle
bye.
un peu
Thank you very
français
much.
pour que les gens s'habituent.
Goodbye.
Bye.